what we're trying to do essentially is recreate the human body in all of its biofidelic realism, if you like. So everything from the tactility of the muscle tissue, the variability between different types of tissues, soft tissues, hard tissues, the position within the human body, the morphology. But more interestingly is what these outputs mean in an actual sense of an output. So essentially what we're trying to do is replace human cadavers and animal substitutes or surrogates with realistic experience for the surgeons. So part of that essentially entails lots of different things, but the most essential part of it really is looking at the CT data. So everyone knows what a CT or an MRI image is. We take that imagery and we reconstruct it digitally using software, different types of processing techniques that I can't really go into, but essentially once we've got that digital image segmented, cleaned up, we're able to then 3D print that image and then use tooling and manufacturing processes to sort of expand that. I'm going to have an image coming up in a second, but you can just see in the corner a little flavour of what's going to happen in a second. What you've got here is a kind of an overall of surgical feedback on what they interpret the materials to be. In this case, it's the human heart. And you can see the 17 different hardnesses within one organ. So this is the sort of detail that we're looking at when we're trying to represent a living organ. In fact, a lot of our research points to using cadavers actually teaches incorrect techniques when you're trying to teach surgery. So as soon as you open up a chest, for instance, of a patient in a thoracostomy, then you see in a cadaver almost nothing because everything's deflated and flaccid and morbid. But in a real living person, there's lots of fluid going on, everything's inflated, it looks very colourful, if you like, and you're going to see that in just a second. So this is an early prototype that we did of a 6-year-old's heart. You can see on the left, this was the stripped back digital model. On the right, this is the sort of fleshed out simulation, if you like. So digital model, silicone simulation. So this is a collaboration we did with King's College London, the biomedical department. And we're looking to simulate a co-articulation, which is narrowing of the descending aorta in a patient-specific study. And part of this, the culmination of this research, basically we were able to pinpoint and justify things that they were talking about in the medical world, which they would never be able to simulate before, not only because of ethical issues, but other types of peripherals going on around it. I mean, you couldn't exactly do this on the living patient because they're very poorly. So able to take the scan data, recreate that, and then synthesize it in materials which mimic the living properties. So the elasticity, the hardness, the flexibility, all those things that make up that tactile experience of actually touching a real living organ, or in this case, a vascular system. So this is kind of where we're at the minute. We're simulating the thoracic cavity, so we've got heart, lungs, the vascular system, even some of the airways, with kind of an overall view, really, of making these things affordable. We have to limit the fidelity. So maximum fidelity, minimum technology. So there's nothing plugging into it, there's no wires, there's no sensors. It's literally all simulated. So what we've got here is a life cast of a living person made by Trauma Effects. It was then cast in silicone. You can see the internals here. This is in progress. And then, hopefully, this video is going to work. Will it work? It will work. So this is the finished simulated trauma surgery trainer. So this is all simulated. This is not a real person. Let me just reassure you. Okay. So you can see here there's the lungs are operational, the heart is pumping, there's a working vascular system, so if you nick an artery at any point, you're able to then suture it. You can stitch this thing together, you can heal it up, literally just in a matter of minutes, really, you're ready to do this entire process over again. So not only is it repairable and reusable, but it's also maximum fidelity. So every aspect of the living person's anatomy is represented. And it's not just a craft exercise, this is craft underpinned by science. So what we've essentially got is all of the data taken from a living person, from that CT, and then we've developed that, processed it, so then we can recreate it using craft techniques, using manufacturing techniques, using the experience of surgeons, but also, this is all meaningless if you don't design it around a user. So right from the very beginning, our main focus was asking the user what's possible, what would you like, what is usable, and how we can actually make this thing even more real. How can we expand this to become a fully simulated body, which you literally can stick in 2 suitcases, take around wherever you want to. Couldn't imagine the look at customs if you get searched, but the idea is to make this thing, you could take it to the street outside and practice major trauma surgery. You can stick it in a helicopter and practice these procedures whilst in the air. You're not tethered to any kind of environment or power source to make this thing work.